In this practical lesson, you will learn about engineering blazing fast similarity searches with HNSW. When your dataset grows from thousands to millions of vectors, brute force or exact searches become a performance bottleneck. Each query requires calculating the distance to every single row in the table, leading to high CPU latency. HNSW, that is Hierarchical Navigable Small World, is the industry standard solution for approximate nearest neighbor search. How HNSW works? HNSW builds a multi-layered graph index that allows the database to jump across the vector space rather than scanning it linearly. The index consists of multiple layers. The top layers have few nodes for long distance jumps, while the bottom layer contains all vectors for fine-grained local search. The traversal, the search algorithm starts at the top layer, moves to the best neighbor and drops down to the next layer to refine the search. The trade-off: by giving up a tiny bit of precision, you gain massive improvements in query speed. Now let's see the comparison between brute force versus the HNSW. As you can see, the comparison is based on various features like search time, precision, scaling, and memory. So as you can see, HNSW is the appropriate search mechanism to search from millions of rows. Let's see the scenario and do some practical task here. The scenario is you are managing a vector store for a global e-commerce search feature. You have 1 million product vectors. The current select queries are timing out under load. Your goal is to implement an HNSW index to bring latency down to sub 100 milliseconds. So the tasks that you need to perform are: first, analyze the table structure, then apply an HNSW index with a M value of 16, that is number of links per node, and EF underscore construction of 64, that is for build time accuracy. So let's see the SQL code here. So make sure that you create this product underscore vectors table if it's not already existing in your database. Then you need to create the HNSW index on the product underscore vectors table. So as you can see here, this is the SQL query to create the index on product underscore vectors table. As you can see, the M value has been specified as 16 and EF underscore construction value is specified as 64. The second step is to tune the search accuracy for the current session. So as you can see, we are setting the HNSW.EF search parameter to 40. So a higher value of EF underscore search parameter denotes more accuracy, but it slows down the execution. The last step here is to run the optimized search query. As you can see, this is the optimized search query that you need to run in the PSQL command line interface. Few best practices that you need to follow and keep in mind. First one is accuracy trade-off. Increasing HNSW.EF underscore search parameter improves the recall but increases query latency. So you need to always test your threshold for applying the value of this EF underscore search parameter. Second is build time. Larger EF underscore construction values create higher quality indexes but takes longer to perform initial create operations.